Well, good morning, good afternoon, good evening, everybody. Welcome to the Vegan World 2026 Moonshot Podcast. And today we have a special doubleheader for World Water Day. And we are honored and delighted that Professor Gerald Pollack has joined us. He has written an amazing book called The Fourth Phase of Water, which I think has a rating of 4.8 or so on Amazon after, 600 odd reviews, which is amazing. Because usually someone or the other comes in and starts putting negative reviews on. But your people are thrilled with what you have done and with that book. And when I saw that, I downloaded it right away. Okay, I haven't read it yet, but I did download it yesterday. So, welcome, Dr. Pollack.
Well, thank you. I'm delighted to be with you and happy to talk about the fourth phase of water or anything even remotely related to that. Thank you for
Wonderful.
accommodating me.
So, what is the fourth phase of water?
It's a phase of water that we didn't learn about when we were in middle school. We learned that water had three different phases. The obvious ones: the solid phase, which is ice; the liquid phase, which we drink; and the vapor phase, which is in the atmosphere. Uh,
Hmm.
However, what we discovered was that there's another phase, and this phase is is it's a kind of crystalline phase where, unlike the liquid phase, where the molecules are ordered in some distinct way, and this is not just a laboratory curiosity. It's the water that fills our
Hmm.
bodies, and it's the water that is essential for weather and for the formation of clouds and such. It's all over the environment. It's not that just a sort of, as I said, laboratory curiosity, but it's all over the place. It's just that we hadn't recognized it. On the other hand, various scientists in the past had recognized that there's something distinct, particularly about biological water, and
Hmm.
and one of them was the guy who many people consider to be the father of modern biochemistry. That's Albert St. Georgi, who won a Nobel Prize for discovering vitamin C, but went on to deal with so many aspects of biological thinking. The guy was amazing. He was a Nobel laureate, so to speak. And
Hmm.
one of his famous remarks was, "Life is water dancing to the tune of solids." It's kind of
Amazing. Yeah.
yeah, and I believe he was right. And he knew that water was absolutely central to all of life. And another was Gilbert Ling. Ling was he died recently at age just shy of 100,
Hmm.
and he professed for many years and in many books that the water inside the cell, particularly, was not liquid water, not exactly liquid water. It was water whose molecules were organized, sort of stacked,
Hmm.
like soldiers at attention. He had enormous evidence to support that, but he was rejected by the establishment, and I think he never quite rose to the level that he should have, or his
Hmm.
ideas, I should say, were never accepted in the way that they ought to have been accepted based
Hmm.
on the evidence he had. So our own work built on the shoulders of those giants, um, and we've been doing experiments now for maybe 20 years, and we discovered much more about the so-called structured water, which is what it was called. That is, as opposed to ordinary water, liquid
Hmm.
water, where the molecules are bouncing around furiously many times each femtosecond.
Right.
This is distinctly different. Here, the molecules in some way are organized, and we found that that it was not exactly as Gilbert Ling had professed. It was close to it, but not exactly. In 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 this fourth phase of water, we found that the water actually undergoes a radical transformation when it's next to certain hydrophilic or water-loving surfaces.
Hmm.
It undergoes a transformation. Those randomly oriented, bouncing around water molecules, they transition into a honeycomb sheet. And
Mm.
when you read my book, you'll see the evidence for that. And this sheet builds next to the hydrophilic surface. And this sheet is hexagonal, a sheet with hexagonal motif, which is very common throughout nature, especially biology. That forms the template for the buildup of the next sheet, which forms the template for the buildup of the next sheet, et cetera. And these sheets build up one by one.
Hmm.
And as the sheets build up, the way we discovered this at first, we knew that when you have something that's crystalline-like or ordered, it tends to exclude solutes. It's sort
Right.
of like ice. When ice forms, it forms a pure crystal, so that any contaminants that had been in the water originally, they get shoved out, and then
Right.
therefore you get a pure crystal instead of a crystal with contaminants. And it's the same with this kind of water. So when we originally detected it, we put some material with a hydrophilic surface into a water that contained little particles, little spheres called microspheres. And we looked in the microscope, and we could see that next to the surface of this material, it was a gel originally,
Hmm.
next to it, these microspheres would be pushed out of that zone. They would,
Interesting.
yeah, they migrated out. Um, and therefore we gave this phenomenon, which we began to discuss with many people, but we didn't have a name. And an Australian colleague suggested, why don't you call it the exclusion zone?
Mm.
And the water inside is exclusion zone water. And it had great advantages because it described what we saw in the first year or two.
Hmm.
Um, and it's easy, exclusion zone, easy to remember, except that it doesn't work in many countries because instead of the Z, it's a Z.
Right.
So EZ zone doesn't exactly have a ring to it, but easy is easy to remember. So
Right.
so if you don't mind, in our discussion, I may be referring to this fourth phase water as EZ water,
Hmm.
but really, the fourth phase is a better descriptor because it's a phase that is absolutely distinct from any phase that we learned. So
Hmm.
maybe I should stop there, but there are a few comments that I would otherwise like to make about the properties of this kind of water, but you might have other questions that you would prefer. I'm not sure.
Yeah, sure, sure. So when it excludes, it's so basically, is it the mechanism for purification? So, like if there are compounds that are hydrophobic molecules, do they
Yeah,
get pushed out?
yeah. It is a mechanism of purification, exactly, and we've actually been pursuing that. We've developed a device
Hmm.
that can be used. So you put the water in, and the exclusion zone develops by a mechanism that I haven't yet, or an energy that I haven't yet told
Hmm.
you about.
Right.
It's actually light. It's infrared light,
Hmm.
which is all over the place. Infrared energy. So um, what it does is it builds the EZ, the fourth phase, and then if you collect this fourth phase, it's essentially contaminant free. So if the water that you put in contains pharmaceuticals or microplastics or whatever, the water that comes out is free of that, and it works rather well.
Hmm.
Except that I mean, it works rather well in the laboratory. With one pass through this device, we found that we could get a 200 to 1 separation of clear, distinct contaminant-free water relative to ordinary water. We could separate it um, with good efficacy. But as with most laboratory discoveries, um, to bring this to a practical conclusion is not trivial, right?
Right.
And in between, you can imagine, as people have described it, the so-called valley of death. That valley, the deep valley, exists between a laboratory discovery and a practical implementation. And
Right.
most of the laboratory demonstrations wind up at the bottom of that deep valley. They never get to the practical
Correct.
implementation. And we've made progress on that, increasing, for example, the throughput, but there's still technical limitations that we need to overcome. So
And
yes, indeed, filtration is one of the practical aspects. Also, I need to mention, in terms of practical aspects, besides that, is getting energy, electrical energy from this kind of water. Because what I didn't tell you is that
mhm.
this EZ fourth phase water typically is negatively charged, it's not neutral.
Hmm.
And so, in order to construct this phase, it starts from water. Water is neutral. This phase is negative. So the question you might ask, well, what about the complementary positive charges? If you got
Right.
negative here, where are the positives? And it turns out the positives aggregate beyond this exclusion zone. So
Right.
what you have is an exclusion zone with negative charge and a region beyond the exclusion zone with positive charge. And that's
Hmm.
a battery. And we demonstrated, again, in the laboratory, we demonstrated that you can put one electrode in the negative, one electrode in the positive, and you can light a light bulb.
Wow.
So it's possible to use water and actually sunlight, which contains a lot of infrared energy,
Mhm.
to renewable resources to generate electrical energy. And we're excited about that as well. So I'm sorry I went beyond what you asked, but
No, no, no. That's
you
perfectly fine.
unleash me, I just keep going.
Oh, that's awesome. That's awesome.
It
Yeah.
is.
So, but the question then, is how much energy are we talking about? What is the energy density of this battery that you can create with this?
That's something that is a real challenge to estimate, and we haven't done it. We should do it, but we haven't done it. Sometimes it's a little awkward to answer quantitative questions, because when you try to do that, it's built on a whole host of assumptions,
Right.
and sometimes we never know if these assumptions are valid or not valid, and so I'm sometimes reluctant to immerse myself in these computations, because with the right assumptions you can get any value that you would like to get, or you think the world would be happy
Right.
to receive, and and so we haven't immersed ourselves too deeply in that kind of water, so to speak.
So
Sorry.
all biological water is this kind of water then,
Well, I wouldn't
or
say
is it?
all, but inside the cell, for
Mm.
example, when you're inside the cell, there are many surfaces. There are lots of solids inside the cell, and the surfaces, for the most part, are hydrophilic. The charges are sitting on the surface, and so you have a hydrophilic surface sitting next to water, and it's logical that the water would become structured, or easy, or fourth phase water, and there are multiple indications that that is exactly the case. So your cell or cells are filled with this kind of water. And
Mm.
the way you can tell that most water is fourth phase water and not liquid water. Imagine if it were liquid water. And imagine if one day you're in the kitchen doing some cooking, and the sharp knife, unfortunately, you cut yourself.
Right.
If the water inside your body were liquid water, because of the cut, it would come pouring out like a break in a water pipe.
Right.
For most people, that doesn't happen.
Right.
And so the water is not really liquid water, it's something else. And many years ago, people knew, this is 60, 70, 80 years ago, a guy named, for example, Fry Wösling from Germany, I believe, wrote a whole book about that, the fact that biological water was like a gel, not like
Mm.
liquid water. And fourth phase water has that consistency. It's highly viscous, gel-like, sort of like raw egg white.
Mm.
Um, and 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 that essentially that's the nature of fourth phase water. And there are other indications that the water is essentially highly viscous, gel-like, and it doesn't come pouring out if you cut yourself.
Yeah.
So you know what that means for biology. The fact that most of our water, you know, it's hard to say all of our water. I don't think that's exactly true, but most of our water, it's not just us, but plants as well and other animals, is this kind of water. And beyond that, you need this kind of water for essentially everything that happens inside the cell. Now, I
Mm.
wrote about that not in the book that you've been so nicely advertising, but in fact, my previous book, which is called "Cells, Gels, and the Engines of Life."
Mm.
Um, in that book, half the book is devoted to. I'm sorry for the noise, but it's
No worries. No.
can't turn it off. Um, is devoted to the following concept that a cell, when a cell does what it's designed to do, for example, when a muscle cell decides to contract, okay,
Right.
what happens is before the muscle contracts, the water is all fourth phase water, essentially all fourth phase water.
Mm-hmm.
And when the cell is about to contract, that water undergoes a transition. We say phase transition. It undergoes a transition along with the proteins in the cell from easy water to ordinary liquid water.
Interesting.
And and that permits the process to occur. And
Mm.
then after the muscle contracts, or the nerve cell conducts, or the secretory cell secretes, the water transitions back once again to fourth phase water. So it's a transition from fourth phase to liquid to
Good
fourth
face.
phase. And
Right.
and the deal is, if your cell is insufficiently hydrated, that is, doesn't have enough fourth phase water, it doesn't function properly. So for the muscle cell, for example, uh, if you've overly exercised your muscle, it has difficulty getting back to the relaxed state, which is
Mm.
the energy requiring state to convert it from ordinary water back again to easy water. It requires energy. So your muscle
Right.
then remains in the contracted state, and that's why you have a muscle knot, not enough energy to return it to its relaxed state. And so the water is critical. The easy water. It's not just that it happens to be there. It's critical for essentially everything that the cell does. So
Right.
you know, as I started to say, the presence of this kind of water, it's not just a laboratory curiosity. It's central to essentially everything that the cell does, and beyond that, in terms of weather and other aspects, this kind of water is actually central to all processes. So
Right.
we're excited about
I
this.
mean, I can imagine, this,
Yeah.
like the same thing that you said about cut in our body. If you cut a tree, the water doesn't come pouring out, right?
Ah, that's a good point. I had not thought about that. Yeah, the water doesn't come pouring out. Right. So it's not liquid water. But
Right.
you know, if you read any textbook on biology,
Hmm.
you know, agriculture, what have you, biochemistry, cell biology, um, you'll read in chapter one usually that cells are two-thirds water, and the water is essentially liquid water, like any
Right.
kind of water. And biology is built on that premise. It's like the water is the water in the bathtub. You know, you get in the bathtub, you bathe yourself, and you're bathing yourself in a surround of ordinary liquid water. It's assumed that that's what happens in the cell, that the important molecules of life are surrounded by ordinary liquid water.
Mm.
The evidence is decidedly against that, and therefore, in terms of building an understanding of biological function, if you start with the wrong premise, the wrong foundation, it's difficult to build a genuine understanding of what happens inside our bodies.
Right, right. So tell us about how weather is influenced by this
Well,
easy water.
okay.
Yeah.
I yeah. So I start by saying what one person who was deeply involved in weather whispered to me on a podcast where we were both being interviewed, and it was during a break, and he whispered, he said, I'll tell you, the people involved with the physics and understanding of weather, there are two things that they don't know at all. And one is how evaporation occurs, and the second is how clouds form. And since evaporation and cloud formation are central to all weather, um, if you're missing the fundamental foundations of all that,
Okay.
it's kind of hard to build a theory, a model from the ground up. One that answers the question of how and why, not just here's how it is. And it's difficult to find such a model. So let me address a couple of things. First of all, evaporation. Well, we're taught that evaporation occurs when a water molecule gets a kick of energy, potential or kinetic energy. It gets energy, and then it rises from the water because of that kick of potential energy. But the questions arise how and why, and I've seen no evidence. It's just basically a conjecture that, we know there's water that gets from the reservoirs on the Earth up into the atmosphere, and how else can it occur other than something like that? Well, there's very simple evidence that you've seen, especially if you frequent Starbucks, which I'm not sure that you do, but or equivalent. It's
I
okay.
drink this, infused
Well,
water.
there you go. You're smarter than the rest of us, but I live in Seattle, and Starbucks was born in Seattle, so um, you know that's so. If you go to Starbucks and you look at your neighbors or yourself drinking some hot coffee, and it happens that the background is somehow dark, what do you see? Well, you see essentially steam rising.
Right,
We've all seen that,
right,
but not too much. Too many of us have thought about what that implies or what it means. Well, what it means, if you can see it, the only way you can see something is if the particles uh, are scattering light,
right,
scattering light from somewhere, scattering to your eyes, then you see it. However, it's well known that in order for light to do appreciable scattering, the scattering particles need to be larger than the wavelength of light. So it means the wavelength of light is, on the order of half a micrometer or something like that. It means that
right,
the evaporating entities must be at least a micrometer or so. And people who
right.
actually measured it, typically it would be 30, 40, 50 micrometers.
Mm.
Now, 30, 40, or 50 micrometers, or even 1 micrometer, consists of a gazillion water molecules,
Right,
right? I'm not ready to do the count, but it's not
right,
one.
right,
And so you have clusters, essentially practically infinite clusters of water molecules rising at the same time.
right.
That's not the same as what we're taught, one
Yeah,
molecule at a time. It's the reason we don't see the air, because the air consists of independent molecules, and they don't scatter a whole lot of light, and so we don't see them. We see right through it. No
right,
scattering. So that if you start with that premise, then a lot of questions arise. Hey, this is rather interesting. We studied it. We published a paper. There's an extensive discussion in the book that you have right on the screen,
hmm,
um, and so we understand how all of this is occurring, and it's occurring in a distinct fashion. The higher the temperature, the more the higher the rate of evaporation, and it seems to occur at a bolus at a time. So you get one blob, and then another blob, and then another blob, and they follow after one another. And each blob is the size that we mentioned. So this is at least one part of the evaporative process. And then if you're at Starbucks and you watch this vapor rising, it actually disperses. And what that means is the little blobs that make up the evaporative contents, they kind of break apart and they
Mm.
occupy the atmosphere. And if there's a lot of that, if you live, for example, in a very humid place, like, for example, summer in Philadelphia or in Kyoto or um,
I grew up in Chennai, India.
it's Chennai. Okay, I visited Chennai, but I'm not sure what it's like in the summer. But I could imagine it's probably
It's
hot and
very
humid.
humid.
Yeah, yeah, okay. And if you remember in Chennai, if you look at some distant structure, perhaps at Mahabalipuram or something, uh, so some distant structure, if it's humid, the distant structure is kind of fuzzy,
Right.
right? Yeah, and when it's not humid, it's very clear. But so why is it fuzzy? It's fuzzy because these blobs, we call them vesicles, these blobs are filling the air,
Hmm.
and they scatter light. So the light that's coming from these monuments or buildings that are far away gets scattered multiple times, and by the time it reaches your eyes, it's been scattered so much that the clarity is lost. You can
Right.
kind of make out the images, but not so clearly. So this is what humidity is. Humidity consists of these vesicles, blobs, or of vesicles that fill the air. So
Hmm.
now, how does a cloud form? Well, cloud forms, as I describe in the book and describe the evidence. And these are actually, we found that these blobs are negatively charged.
Hmm.
And of course, negatively charged particles resist coming together to form anything, right?
Right.
They repel each other. Both of us began our careers in electrical engineering, and
Right.
this is about as basic as you can get. So, what you need is you need positive charges somehow
Hmm.
to bring these vesicles together to form a cloud, and those positive charges are the second half of the evaporative process. I'm not going
Hmm.
to describe how because I need a few illustrations and such. But you have these blobs that are evaporating more at higher temperatures, and you also have the positive charges evaporating as protons or hydronium ions. When
Hmm.
these two come together, and there are certain circumstances that allow them to come together, um, then a cloud forms, and these positive charges draw together the two negative charges, and this is um, a situation that has been elaborated in detail by the legendary physicist Richard Feynman, the Einstein of the second half of the last century, who called it like likes like.
Hmm.
So you have like charges, the blobs have negative charges, and
Right.
they like each other, so they come together. He said like likes likes because of an intermediate of unlikes. So you have
Right.
a positive charge in between, then the negative blobs will or vesicles will come together. They won't actually join each other, but they'll stay at some distance that is
Right.
defined by the attractive force. When that attractive force of that positive charge pulling them together is equal to the repulsive force of blob repelling blob, then they're
Right. Right.
stable. That's a cloud. And if you start with that, you can begin to understand many phases or many aspects of weather.
Hmm.
They come together, I think, in a very natural and understanding weather, and including an understanding of hurricanes, tornadoes, the iconic figures of tornadoes, even the twisters.
Hmm.
Uh, so um, I obviously nobody can be certain that this is a hypothesis. I think it fits
Right.
together nicely, but we will never know if it's really is adequate. But it explains an awful lot, and
Right.
that's going to appear in detail in the book that um, that's coming as soon as I can get my artist son, who is responsible for all the artwork that you see in the fourth phase book. And we've gotten so much positive feedback on that. He's a really, really gifted artist. He's busy dealing with remodeling his home. As soon as he's finished, he's coming back to the artwork, and the book that's coming will be published, hopefully before the end of this year. So
Wonderful.
anyway, I've given you a long discourse, and it's a challenge to do that without some diagrams, but
Right, right. No,
I try.
I understood exactly what you're saying. So
Oh,
thank
thank
you
you.
so much.
Thank
Yeah,
you. Thank you.
very well done. So uh, these blobs that rise up and that are negatively charged, and then they meet through. So they basically you're talking about the nucleation of this positive charges that use that. And you use that to bring multiple blobs together to make a
Yes.
huge droplet, so to speak, right?
Right. Absolutely. Yeah. Yeah. And they can grow like, for example, a cumulonimbus cloud,
Mm,
tall clouds, and they form over warm oceanic areas. And we know that the warm areas generate these blobs much more rapidly than cool areas, and the
right.
water is infinitely available over the ocean. So you have all the ingredients that are necessary for forming these giant clouds. Um, and,
One,
and and so and it also it allows you to understand why you can sometimes get one cloud atop another. You can get a stack of clouds,
mm,
and that actually um, has to do with the fact that the clouds are in essence negatively charged because the blob's negative charges outweigh outnumber, if you will, the number of positive charges needed to bring those vesicles together. So the cloud has a net negative charge. The Earth has a net negative charge. This is not widely taught, but I know that in Russia, for example, students know about this. They learn it in middle school.
mm,
So, yeah. So they know that the Earth is negatively charged, and you can read it in, for example, Feynman's Lectures, Volume 2, Chapter 9. It's all devoted to the evidence that the Earth has a negative charge. So if the Earth has a negative charge and the cloud has a negative charge, you get a repulsive force, and that's what keeps the cloud up in the sky.
right,
Otherwise, it would come plummeting down because water is more dense than air, you know.
right, right, right,
So the cloud stays, and it's also why you can get stacks of clouds, because if one cloud has more negative charge, the repulsive force will be greater and the cloud will sit higher. So you
right.
can get a stack of many, many clouds
Mm-hmm.
using that formulation. And there's one other that I just can't resist. Maybe because I understand that you have a background in electrical engineering, and so you will have encountered induction, Faraday induction.
Right,
And so if you have let's say you have a positive charge or negative charge here, and you have a surface beneath, that negative charge will induce positive charge on the surface,
right. Mm-hmm.
right? And the two will be attracted as a consequence of that. So I think that is what happens during when a cloud decides, so to speak, to rain. When the cloud gets low enough, that is, if the negative charge has diminished,
Mm-hmm.
so it is lower. When it becomes close enough, the induction effect becomes profound. And so you have a negatively charged cloud, though less negative than one that sits higher up. And it'll induce positive charge here. And that will bring the cloud down further because it's an attractive force. And when that attractive force gets big enough, it will pull the individual droplets from the cloud.
Right,
And that's why it rains in droplets rather than like unzipping an entire cloud and letting the bathtub of water come plummeting down on our heads.
Well, I have felt that too in Mangalore in India. I felt like someone is pouring from a bucket. It's really
Well, yeah, the rain could be heavy enough, and in fact, in this explanation, the rain is actually the droplets are actually pulled. They're drawn from the cloud. They're not just released from the cloud. And there's evidence for that because, and I don't know if this is in Mangalore or something, but areas where you get pounding rain. Yeah.
right.
So a group of scientists measured the rate of fall of raindrops. They
Hmm.
actually measured it. They were using high-speed video. And, you can calculate if you have a freely falling droplet, if you know the size and density and whatever, you can compute the terminal velocity. Well, they actually measured this, and it turns out to be up to 10 times higher than the theoretical free fall velocity. And their conclusion was those drops are somehow pulled from the sky.
Right.
But they couldn't understand why. But I
Right.
think induction is the reason. The inductive force pulls those droplets, and that's how you can get pounding rain.
Right. 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 Fascinating. So
I think so too. It's so exciting to,
it is. It is.
one never knows if one is on the right track, but um, the evidence seems to fit. So
Well, that's the thing with science, right? You can hypothesize and then you can verify that it isn't broken. So
well, yeah, that is the truth. Of course, you can never prove anything. All you can do is disprove it. And so, um, you know, um, but I mean, that is in essence my goal. If to put forth a hypothesis, and there are many people who have methods of investigation more sophisticated than what we have in
mhm,
my own laboratory, who, if interested, could investigate some of these things and, perhaps prove them invalid or, have evidence that is supportive. But the bottom line is we really need to have a hypothesis, theory, whatever, that starts from the essentials of physics and builds up from there, not
right,
an ad hoc kind of explanation.
right.
And that's I believe has been missing from this field for a long time.
I
If those people who are interested in the climate issue, it seems rather self-evident that in order to approach this issue in an informed way, you need to know something about the physics of what's going on. And
right. Yeah,
so
yeah.
if the premise that we've been developing turns out to be invalid, then another one needs to be developed in its place. But there's a really desperate need for an understanding of how weather actually occurs.
Right, right.
Um,
Absolutely.
yeah, so we're trying.
Thank you for your contribution. I mean,
Sure.
does evapotranspiration also work the same way from through the leaves? How does water?
Yeah. Um, essentially, essentially the same. And obviously, it contributes quite a lot to the humidity in the atmosphere. Um, uh, and so it needs to be understood. But I think the real challenge in terms of plants is not the understanding of transpiration, which should be rather similar to what I've been discussing, but one of how the water gets from the roots all the way up to the top. So,
Mhm.
um, as you know, better than I do, I'm sure, some of the trees are 100 meters tall. Um,
Right,
you got some in California, and
right.
even a few in the Northwest where I live. Um, and it's like the xylem vessels uh, can run all the way from the roots up to the top. And if you have a pipe that's full of ordinary water, it's a lot of pressure at the bottom of that pipe. So how does the water wants to go down, not up, but it goes
Right.
up. How does it do that? And we think we understand this because uh, and it has to do with the fourth phase of water, and that's also described in the book, that this fourth phase of water book that you're illustrating. And the
Mhm.
process relates to easy water. I won't attempt to describe it. It's not complicated, but it's helpful to have a few diagrams to do it. And I think the energy for driving the water up, it comes from light, comes from especially infrared light, which builds easy water, which separates charges, and those
Mhm.
charges are critical for driving the process. So
So
yes, long answer to your short question.
yeah, in a way, you're telling me that easy water or the fourth phase of water, it's basically a store of infrared energy. Basically
Yes.
converted infrared energy into something and stored it.
Well,
So
yeah, I mean, I would look at it, I would state that a slightly different way. I would say the energy comes in and the water is a transducer that transduces that energy into a different kind of, say, potential energy. And that
right,
potential energy is ready to be delivered in many ways.
right, right,
Yeah.
and that's uh, basically the principle of your battery as well. You know,
I'm sorry, the principle of,
the battery that you're talking
yeah,
about is
yes,
connected
absolutely. Yeah,
positive, negative.
yeah, yeah.
So the water is H3O2. No,
H3O2.
H3O2. That's the crystalline honeycomb structure that's formed.
That's right. And yeah,
And then you have hydrogen molecules outside. Hydrogen,
oxygen molecules. I'm sorry, hydrogen. Yeah, excuse me.
hydrogen,
Yeah, you have protons essentially,
protons,
not
essentially.
hydrogen molecules, but protons.
Protons, yeah.
Yeah, yeah. So and the protons are maintained outside. You think that they would recombine because you got plus and minus, but
Right.
the energy that's coming in keeps them separated from one another. And
Interesting.
so it is genuinely just like a battery. Yeah. It's
Yeah,
nature's
battery,
nature's prime battery, I think.
typically in a battery, there is a membrane or something that separates the anode and the cathode, right? So it's
Well, in this case, the membrane, it's there's no membrane here, and what separates it is that these protons actually latch on to water molecules, forming hydronium ions.
ah,
So this is well known. The hydronium ions are too big. They can't penetrate back into this honeycomb lattice, so they stay outside, even though they really want to get back in because their positive charges would like nothing more than to to get back to the negative counterparts, but they can't get into this lattice. These hexagons and the honeycomb lattice are too small to admit them, so they stay outside.
fascinating. So which
I
means that membrane is then real, basically very, very thin, right?
well, you could
Right to
you could
track, right?
you could call it a membrane. I guess it is a membrane in a sense, but it consists of many layers, not just a thin
Right.
layer.
Mhm.
Yeah. So, but yeah, can't get back in.
Right.
Of course, if you have enough of them trying to penetrate, the pressure is so great that they will invade the lattice. And it turns out, it's again, I don't have the diagrams to show, but when that happens, you get ice.
Hmm. Interesting.
We have evidence for that,
Mhm.
but it's a little bit challenging to describe without that. But you can imagine, ice also has a hexagonal motif to it. Easy water has a hexagonal motif. And we found that if you want to convert water into ice, you don't go directly from liquid water to ice. You go from liquid water to easy water, which has a hexagonal motif, and then to ice. And if you
Interesting.
want to melt the ice, you go from ice to easy water, again, a similar but not the same hexagonal motif, and and the protons or hydronium ions are then excluded.
Right.
And then you go from there to liquid water. So it turns out, again, described in the book, that there are many anomalies that arise if you try to understand how ordinary liquid water transitions directly to ice, but it doesn't. You see, and I show in the book and various publications that those anomalies disappear if you understand that the real pathway is from liquid water to easy water and then to ice, and vice versa when you melt the ice. So
Right.
it's another one of those fascinating features, fascinating to those who are interested in mechanisms. Uh, and these understandings go a long way, or these revelations, I should say, a long way toward a general understanding of nature. And this is what is so exciting.
Yeah. One last question for you before we
Sure.
close. Over the last 10,000 years, humans are estimated to have cut down half the trees on the planet.
Wow.
Okay, so we've gone from about 5 to 6 trillion trees to about 3 trillion trees today.
Wow. I didn't know that.
So if we restore those trees that we cut, not only are we storing extra carbon from the atmosphere, we'll also be storing all this water as easy water in biomass. So uh, I'm just thinking about, okay, how much potential energy is being stored there? That, you know, because if you just look at the albedo effects, you may think, oh, bringing back the forest will actually heat up the planet because it's going to absorb sunlight. And I'm saying there is something else that's missing here because I know that a forest is cooler than in Phoenix, where I live.
Yeah, the forest is cooler, and
Right.
this is not your question, but or
Yeah.
maybe way to your
So my
question.
question is, do we have an idea of how much? I mean, is that enough to compensate for the melting of the Arctic if we brought back the trees? That we could.
I can't comment on that. I've never thought about that issue.
Hmm.
I I don't I I haven't immersed myself at all in the issue of climate change, and
Hmm.
one of the reasons is that it's so infused with political issues that I'm reluctant. Yet I understand how critically important it is, and I just have one comment that is, in terms of temperature, and how we sense heat and temperature, is that we found that you know. Um, if something radiates a lot of energy, it feels warm to us. If the molecules are moving around and there's a lot of infrared radiation, we sense that as heat.
Hmm.
Okay, if the molecules are not moving around, as in ice, for example, um, and easy water, we found it feels cooler. So the more easy water we have in our environment, the cooler we'll feel. And in fact, the Romans did unknowingly use that to keep cool. And in the summer, they would have some hydrophilic surfaces, and they'd pour water on it. And we know now that these hydrophilic surfaces build easy water, and the easy water, experimentally, we found doesn't radiate very much energy because the molecules are not moving around a whole lot, so it feels cooler.
Hmm.
Well, the same principle ought to apply in the trees. If the water is easy water, which I think mostly it is,
Hmm.
just as it is in us, then the trees are not going to be radiating a whole lot of infrared energy, and it'll feel cooler. And I
Right.
think that's the reason why it feels cooler when there are trees than when there are no trees. So
Right.
I think you're onto something. Quantitatively, I have no clue uh, about
Right.
that. I've not thought about it, but you have, and you may be onto something really important.
Thank you so much. On that note,
Okay.
we'll
Well,
end the
thank you.
broadcast. So, yeah.
Okay.
Do you have any other things you want to tell us before we close?
Well, yeah,
If I didn't cover anything
I
else.
guess I just want to say maybe my mantra about the truth in science, and unfortunately, the way science is conducted today, it's a
Hmm.
real challenge to find foundational truth because you're up against an establishment um, that thinks it has already discovered truth, and those who challenge it. It must be nutcakes or something, crazies or whatever. And it's true of, unfortunately, not all scientists by any means, but enough.
Hmm.
And therefore, it becomes really hard for those scientists who are interested in ground truth, in identifying ground truth. It's difficult for them to make headway to get support. And
Right.
we've actually founded a foundation. It's called the Institute for Venture Science to try to support with funding those scientists who are pursuing ground truth and whose ideas have been very thoroughly vetted. We want to give them an opportunity for their ideas to see the light of day. And anybody who's interested in that, please don't hesitate to contact me. Um, this is an important feature. It becomes more and more important today when it's really sometimes difficult to know what's true and what's not true, and the forces that oppose the emergence of ground truth. So anyway,
It's
that's
called the Institute for Venture Science.
Institute for Venture Science,
But
ivs.org. Sorry, ivscience.org.
okay,
IV as in intravenous, or Institute for Venture, ivscience.org.
okay, I'm going to post it on the chat. So
Thank you. Or just contact me.
yeah, wonderful. Thank you so much, Dr. Pollack. It's been an
Thank
honor.
you,
I could
Salesh.
talk to you for hours.
Well, it's very interesting. And thank you for the opportunity. Happy World Water Day.
Thank you.
Okay, we'll see you.